Everyone, and welcome to this module on Introduction to Continuum Mechanics. So basically, this is the first video of module 4, or the last module in this series of continuum mechanics. And this is basically chapter 7 of the book. And we are not going into something new, so it's again the field equations, all 5 field equations, but we're approaching them in a different way. We're using the Reynolds transport theorem and to derive these equations here, and let's just solve some problem based on this theorem. So we already discussed the differential and integral form of the field equations, which are referred to the local and global principles. So before getting into the derivation of the field equations, we need to get to know some of the basics or some of the fundamental theorem. Uh, so you already get to know the divergence theorem in the last video of module 3, or in the last part or section of chapter 4 of the book. So now we're going to actually discuss the Green's theorem, which is the two-dimensional version of the divergence theorem. So basically, in divergence theorem, we had this 3D surface, or the volume, that we just converted into, let's say, the surface, or the two-dimension. So we had the integral over the volume, and then we converted to the integral over the surface. So now in Green's theorem, which I already mentioned is the two-dimensional version of the divergence theorem, we have this 2D, let's say, domain. So the integral over this 2D domain is going to, so we're going to convert it into an integral over the curve that encloses that that surface. So it's like you have an arbitrary kind of surface. So it's like the divergence theorem before doing this. So if you have a volume, let's say that this is volume, like volume. So the divergence theorem, we moved from volume to the surface, and here we have an arbitrary surface, and there is a curve like C that encloses the surface. So we are moving from the surface to the curve. And this is basically done using the Green's theorem. So Green's theorem basically states that if you have a function like p, which is a function of both x and y, so it's a multivariable kind of function, and it also has it is continuous. So we have the partial derivative of x with respect to y, and the partial derivative of p with respect to with respect to x, and then with respect to y. So this function is continuous and differentiable. Then if we have this, let's say, this domain like R in here, which is enclosed by a curve like C, and there is a normal to this curve like N, where we define this N basically as nx ex plus ny ey, then we can write the Green theorem in the form of the integral of partial derivative of p with respect to x here. So this one, so let me just put a comma in here, on the domain R. So here we have a surface is equal to the partial derivative of p dy over the curve C. And this dy is basically a function, because here we have, a part of the curve where we can call this as ds. So this ds is a function of both x and y. So you can see that it has, let me just draw this using another color. So if this is, for example, this is our coordinate, this is x, and this is y. So this is going to be dy, and this is going to be dx. So then we can write y as a function of x, and x is also a function of x. So we can write this as integral of p instead of y, so we can divide and multiply by ds. So then we can write this as an x ds over c. So let me just shift this a bit to the right. And also, you can write the partial derivative of p with respect to y over r is equal to p dx, of course minus, and then we have here over c. So we had the region, the integral over the region is equal to the minus of the integral over the curve when we have a partial derivative of p with respect to y. So this is equal to the integral of p and y ds over c. So here the book actually wrote these two equations basically in two different equations, but some of the books basically combine these two together. So they write that integral of the partial derivative of p with respect to x minus partial derivative of p with respect to y equal to this equation. And I have here we integrate over the domain dA, of course. I forgot to include this. And this dA is basically in here. So we have dx, and of course this is, say that this is dr, so this is dy. All right, so let's get to the proof of the Green's theorem. So the book actually used a kind of arbitrary Blake ellipse for the representation. So we follow the same. So we have an oblique ellipse in here. So then we have the y-axis, and then we have the x-axis. So the book actually said that if you have, let's say, the lower part of this is A and the upper part of y as B, then we denote this as, let's say, A, and we denote this as B. And we also have the lower part of the lower bound, it's better to say, of x. So we call this, for example, E, and we can call this D because I reserved C for the curve. C is counterclockwise in Green's theorem. So basically, if you look at this, let's say that this is your eye and you're looking at this side view, looking at this side view to the ellipse. So here we can say that you have two parts. So this is the yellow part, and we also have a blue part in here, where basically the blue part is x1, y, and this part, the green part, Let me just write it with another color that you can distinguish. So maybe get rid of this and just change it with another color, red one. Right, so this is x to y equation. So if we select, so this is basically R, the region is R. I'm not going to write it down in here. And we have an element here where we have dx, and here we have dy. So this is basically dA. And this is your I. So let's say your I. And I'm going to write the partial derivative of p with respect to x dA over the region R. So why I did this, it's like, let me just break this into two integrals because we have over dA. So we have dx, dy, partial derivative of p, and then with respect to x. And here I'm going to write the bounds in here, the range. So for this one, since we're looking at this, so we have two equations in here. So we have to write this equation, the upper bound, based on y, and then we will have based on y. So it's like, the equations of circle, like x1 plus x2 is equal to 1. If you have something, for example, let's say you have an integral, and for example, it is bounded between a value of y of -1 and, for example, 2, then you're going to write some function here. This is like p of x and y. And since here we have x, so we have to write the bounds based on the y. So we have, for example, 1 minus y squared minus, and the square root of 1 minus y squared. So because because x here comes from plus minus of 1 minus y squared. So the lower and upper bounds should be written based on y. Then they are integrable with respect to y. So it comes from this concept in here, so it's not something new. So then we have this integral. So for x, it is between x1 y and y because we are going to replace y into x1 to get a final function based on y. Then we can integrate this integral with respect to y. So from x1y to x2y, and the lower bound for y is from a to b. So the lower is a and the upper is b here. All right, so now we have this in here. So this integral of from a to b of x1y, then we have x2 y partial derivative of p with respect to x dx dy. So this can be written as from a to b of, so this partial derivative of p with respect to x dx gives p of x and y from x1y to x2y dy, which is equal to the integral from a to b. Then we have p. So instead of x, we have to write this x1 and x2. So it is x2 y minus p x1 y and then y, and the whole dy. So if we separate these, so we have from a to b of p x2 y dy minus the integral from a to b of p x1 y dy. So this is equal to, so here we have px2y, so this is x2y, this red one in here, and it goes from a to b, so it goes from a to b, so it is in this direction, so it is aeb, right? So we can write this as aeb over the curve aeb, because this is the same as a to b, so this aeb, and p, we have this let's say this function here, so I'm going to write it as p only, minus, then we have this part, which is p of x1y and y, and it goes from a to d and then b, so it is a db, because we are moving from a to b. We are not going to write b da, because that is otherwise moving from b to a. The lower bound is a and the upper bound is b, so we write here a db, a db p dy. I'm not going to write the whole function, so just p, because we know that we are integrating over this region of p. So this is a e b of p dy, and here if you notice, we have aeb, so we have aeb, and then for this one here we have adb. So if I change this adb to bde, then I can integrate over the whole curve in here over c, and it is in the counterclockwise direction. So I'm going to replace this with the minus of, since we have abd, so we basically change the bounds, so this becomes bda, and it has minus sign here, then we have p dy, and this is equal to the integral of aeb p dy becomes p dy over b dA. So we basically are moving from a to e and then b, and then from b to d and then a. So we are basically moving over curve c. Then we have p dy. So the next part is to derive this part of the equation. We have p nx ds. So for this part, let's say that, oops, that you have this coordinate here, y, and then we have x in here. So we have an arbitrary kind of curve in here. So this is just magnified. So we have this ds in here, and this is basically going in the counterclockwise direction. So we have dx in this direction, and then we have dy in this direction. And we also have the normal, which is n here, and this value is n, and we know that it is equal to 1 in here, and then we also have nx and then ny in this direction. So let's say that this is theta in here, so this is going to be theta again. So then what we can write in here is sine theta here is dy divided by ds, so theta is very, very small, and then cosine theta is basically minus dx ds because it is going in the negative direction of x. And we also have, from here, we can write sine theta is equal to nx divided by n, which is 1. So it is nx. And then we have cosine theta is equal to ny. And remember, this is positive, so we write nx. So ny is also in positive direction, divided by n, which is equal to ny. And here, n value is 1. Is assumed to be 1. So if we compare sets of equation 1 and 2, then what we get? So here we have nx is equal to dy ds, and ny is equal to minus dx ds. All right. So now we have the integral of p dy over c. So let's assume that y is a function of s. So it is changing basically, as I already mentioned here, with s, and x is also changing with f. So we have y as a function of s, so I can write p, so I can just write dy times ds, divided by ds, then times ds. So dy ds is nx, so I have p nx ds. And basically, we derive this equation here. So next we have the second part. So maybe just proof, let's say star and then 2 stars. So star, and then we have the proof for 2 stars. So again, we have the same picture here, so the same figure in here. So we have y, then we have x in here. So now we need to basically locate the lower bound of this arbitrary kind of, let's say, domain. This is C on x. So the lower is a and the upper is d. So I call this a and this point is b. And now we're looking at this in this direction. And then it has, its maximum and minimum in here. So I'm going to call this as D, and I'm going to call this as E. So here, if you look at this, so we have this red section. Sorry, I made a mistake in here. We are looking at from this side. So this is your eye, and here, your eye is in here. So you're looking at this from this side. So if you look at this from this side, this is the first curve you see. And this one in here is the second curve that you see. So basically, this is y2x, and this is y1x in here. All right. So basically, if I write the equation, we had a partial derivative of, let me just say it, p with respect to y dA. So we convert it to a double integral, partial derivative of p with respect to y. Then we have dy dx, and here we have y1x, so we plug x into y1, and then we plug x into y2, so we get the equation based on x, and then we integrate over x, so we integrate over dx, so we have the lower bound as a and the upper bound as b. So if I just rewrite this again in here, so we have from a to b, y1 x, y2 x, partial derivative of p with respect to y dy dx. So what we get is the integral from a to b. Then we have p of x and y from y1x to y2x dx, which is equal to, from a to b, p of x y2x minus px y1x and whole dx. So this is equal to, so if I expand this, so this is from a to b, p of x y2 x dx minus from a to b, p of x y1x dx. So here we have y2x from a to b. So this is y2x from a to b. So it is a, e, b. So it is a, e, b. We integrate p dx over a, e, b minus, then we have y1x from a to b. So this is y1x from a to b. So it is a, d, b. So it is a, d, b, p, dx. This is equal to, so here we can write a, e, b as minus b, e, a. So we change the upper and lower bound of the integral, so it changed into a minus sign. So b, e, a, p dx minus, then we have a, d, b, p dx. So it's just moving from b to e, e to a, and then d to b again. So it's like paving the whole c dx, and we also have a minus sign in here. So I can write this minus cp dx, assuming that s is a function of x. So p dx ds over c, and here dx d, let's say it was dx ds was equal to minus ny. So we have a minus in here, and we also have minus ny in here. So this gives us p ny ds over c.